So in this video, we are going to talk about Bayes theorem, which is very important theorem in the probability theory, and which is also having a lot of applications that you will see in the coming next few semesters. Okay. So many times you will be talking about finding a probability of an event given an event has already occurred. Okay, so both way you can look at. So P of E given F or P of F given E. So what is the relation between these two? And that's what the Bayes theorem gives. So it gives a relation between P of F given E and P of E given F. Okay. So what does the Bayes theorem says? So if there are two events F and E, okay, if there are two events F and E, we will take this screenshot to the Microsoft OneNote, and I will enlarge this. So suppose F and E are two events. Okay, F and E are two events from a same sample space. They should have a same sample space, and we also know that P of E is not equal to 0 and P of F is not equal to 0. Then it says that P of F given E is nothing but this formula. Okay, so now we need to prove this. We can easily prove this using very simple formulas that we already know. Okay, so these are the formulas that we will be using. So this is the one part of the proof that I will take it to Microsoft OneNote. Just elongate it, and then yeah. So we know from today's class that P of F given E is given by P of E intersection F divided by P of E. And likewise, if you interchange E and F and P of F and E, then you will get this. So P of F given E is this, and P of E intersection F is P of E given F is this. Okay. So now what this two equation gives is there is a common term P of E intersection F. So we can find what is P of E intersection F from 1 and P of E intersection F from 2, and then we will equate this, and that's what we get. P of F given E multiplied by P of E is equal to P of E given F multiplied by P of F. And so P of F given E is nothing but P of E given F multiplied by P of F divided by P of E. Okay. So now if you see the formula, we have got the numerator correctly. This is P of E given F multiplied by P of F, and here also P of E given F, P of F. Only thing is we need to show that P of E is nothing but this big value. What is this value? Okay. So for proving that P of E is that value, we will use a very simple derivation. What is the derivation? We will see that here. Yeah. So this is the one that I was talking about. So let me put it here. So to derive what is P of E, what we will do is we will so E is equal to E intersection S. Okay, S is a bigger sample space, so if I intersect with S, I will get E only. And S is nothing but F union F bar. F bar is F complement. So if you take one set and its complement union, you will get the universe, right? So it is E intersection F union F bar, and now you apply the distributive law, you will get this, right? So the probability of E, now we are applying the probability function for that. E is equal to this value. So P of E is nothing but P of E intersection F plus P of E intersection F bar. Okay. So now, what is this P of E intersection F? We already know from here, from 1 and 2 equation. P of E intersection F is P of F given E multiplied by P of E, and P of E intersection F is equal to P of E given F or P of F. So we will use one of that formula, that is P of E intersection E given F multiplied by P of F, and we need to find P of E intersection F bar, and that is nothing but P of E given F bar multiplied by P of F bar. That is just replacement of F by F bar, that's all. Okay. So P of E is this value, and that's what we need to show, right? So here that is this value. So that's what we have shown here also, P of E. So ultimately now we have shown, what we have shown is P of F of E is nothing but P of F given E is nothing but the value that the Bayes theorem says, and that is nothing but P of E given F multiplied by P of F given by divided by this value. What is this value? That's the value that we have shown, that P of E is equal to this value, right? So that's what we have written here. So we are able to derive it quite easily. So now coming to the example, how to use this theorem to find some probability, conditional probabilities. That's what we are trying to see in this. Okay. So what is the problem? The problem is given like this. So you are knowing something about a disease which is very rare, okay, very rare disease. So you know that the probability of having a disease when you randomly choose a person in the population is 1 by 100,000. Okay, so that is this value, 1 by 100,000. And the probability of correctness of the test who has the disease. Okay, so there is a person who has a disease. What is the correctness of the test? Like, he has a disease, and the test also says he has the disease. Right? It's a diagnostic test. You can take it as a medical test, or can be any prediction algorithm actually, where there are only two values. Okay, either you have a test or you don't have you have a test which says yes, or you have a test which says no. Okay. Right. So what is the probability of the correctness of the test? That is who has the disease, and the test also says it is yes, and that is 99%. And likewise, the correctness of the test who does not have a disease is 99.5%. Okay. All these three values are given. Now, what is the thing that we need to find is, we need to find the probability of a person who has been tested positive, but what is the probability that he has actually that disease? That's what the problem is asking about. Okay, and that one can be easily found out using the Bayes theorem. But first we need to formulate that theorem so that we can apply it quite easily. Okay, so for that we will get this picture down here, and just along with this, move this down a little bit. Okay, so we are taking two events now. F is randomly choosing a person, and what is a who has a disease, right? And he is test positive for the disease. Okay? So two events are there. Now, what we need to find is, actually, we need to find P of F given E. So E means the test positiveness has occurred, but what is the probability that he will be having the disease? So that is P of F given E, and that is given by Bayes theorem, this. Okay. Now we need to find all these values, P of E given F, P of F, and P of E given F bar, and P of all these values can have to be found out. P of f can be easily found out. What is P of f? You randomly select a person, and what is the probability of having that disease? That is nothing but 1 divided by 100,000, and that is this value. So P of f bar is 1 minus that value, and that is this value. Okay. So now we have found out P of f and P of f bar. So all these values have been found out. Now we need to find P of e given f and P of e given f bar. Okay. So that we can find out. How? We know that just a minute, I will take that screenshot and then upload it here so that it becomes easier for me to explain. So by 2, what is that 2? 2 says that person has a disease. What is the probability that the diagnostic test also gives the correct result? And that is 99%. And that is P of E given F is 0.99. Okay. So if I take the 1 minus of that, it will be P of E bar given F. What is E bar given F? You are having the disease, but what is the probability that the test says he doesn't have a disease? And that is 0.01. Okay. So now we know this value also, P of E given F. But we need to find what is P of E given F bar. Okay. And by 3, what is the third equation? The third equation says P of correctness of the test who does not have a disease. He does not have a disease, and the diagnostic test also says he does not have a disease, and that is 99.5%, and that is 0.995. Okay, so 0.995 is P of E bar given F bar. So if I take the 1 minus of that, then I will get P of E given F bar, and that is 0.005. So now we have found out all the values that we need to find, right? And we need to just plug in those values, and if we plug in those values, we will get this number. So that I will just input it here and elongate it. So you just plug in the value, and then you see that just by some arithmetics you will be able to find the value is 0.02. Actually it is 0.002, so it is 0.2%. Okay, it is not 2%, it is 0.2%. So what does it say? The test is positive, but what is the probability that you have the disease? That is very less. So even if the test says positive, the probability of you having a disease will be this much only. Okay, so that is the thing that we need to find. Okay, so what we have found is this: find the probability of the person who has the disease, who tests positive, who has been already test positive, and what is the probability of that person having a disease, right? That is 0.2%. Likewise, you can also find the probability that a person who tests negative for the disease and he does not have the disease. So the test says it is negative. What is the probability that he will not have the disease? And that is given by, again, the Bayes formula like this. So now we need to find P of F bar given E bar, and that is given by this Bayes formula. So now you can find out what we have found out in the last case, and you can just plug in the formula and then you can find out. Okay, so this I will leave it to you as a exercise. You can do it on your own. Thank you.